Thanks everyone for tuning in. In case you're curious, I'm being backed by Prince in an early version of the Revolution circa 1982. So Prince, give a celebratory. So this work is joint work with some lovely colleagues, Julie Louvrier and Olivier Jimenez. So I'll start with a brief background into species distribution modeling, in particular looking at when we have multiple different data sources. The novelty of this work will be in extending a new modeling framework in this context, having multiple data sources that accommodate for various issues that are common in species distribution modeling. So with species distribution modeling, as Roosbay had said, the aim is to relate species data to the environment to come up with maps of predicted spatial distribution of the species. And depending on the data source that you have, there'd be a different modeling framework that might be appropriate. The ones in blue are the ones I'm going to focus on in my talk. So if you've got presence-only data, you can use a point process model. If you've got a repeated presence-absence data where you've gone to presence-absence sites multiple times, you can use occupancy modeling. Regardless of your data source, there's likely to be some sort of bias inherent to it. And again, the ones in blue are the ones that I'll be focusing on in this talk. With presence-only data, you often run into the issue of sampling effort, where your point pattern reflects not just where the species are, but where the observers are. And as such, it might be such that those points are biased towards sites that are more easily accessible. There also could be detection bias. So perhaps you go to a site looking for a species and it's there, but you miss it. And if that detection probability varies throughout the space, then that can bias your estimates. These are by no means exhaustive lists of either the methods or the sources of bias, but you get the idea, hopefully. So in many situations now, you'll have more than one source of data, and this is what motivated this talk. We were interested in modeling the distribution of lynx in the Jura Mountains in France, and we have 3 different data sets. The orange circles are presence-only sightings in the wild, so someone saw a lynx on a hike, for instance, and reported its location. The green triangles represent domestic interferences, so basically where the lynx have interfered with some tasty livestock. And we see right away that the distributions there, they're both presence only and they're both of lynx, might have different sampling effort. There are a lot of orange circles in the north and green triangles in the south. We also have the purple squares representing the locations of camera traps from which we can extract occupancy data. So if we want to then build a species distribution model, we want to select some variables to include. So based on a review of the literature, we chose 4 environmental variables. We also have variables that we think could help uniquely characterize the bias in each of those data sets. So for the wild sightings, we thought things related to accessibility, so distance to the nearest road and train line. For the domestic interference data, it's really about where those livestock are, so distance to the nearest farm and percentage of agricultural land. We chose distance to the nearest urban area for detection bias for the occupancy data set. Okay, so say this was 7 years ago. What you might do is then pick your favorite of those 3 and then build a model. And what we see is this is what's been done here. The left 2 examples are point process models, so inhomogeneous Poisson point process models. And on the right, we have the data map of the fitted to the occupancy data. And we see we get 3 completely different pictures. So that's not too good. If we want to know where the lynx is, we'll get 3 different stories depending on which data source we choose. Something weird is going on with this occupancy one. This is in units per square kilometer. So 25,000 lynx up here. Woohoo, they're having a party. Something's going on there. So maybe it's not a good idea to just use a single source of data. So some clever people thought that, well, maybe we can incorporate all that the data that we have. So Fithian and D'Orazio both came up with ways to make use of all sorts of data. Fithian, presence only and presence absence, and D'Orazio, presence only and occupancy. The key to these methods is to define a combined likelihood expression, which is equal to the sum of the log likelihood forms of the component data sources. The key to making it work is that each data source contributes to the estimation of common environmental parameters. So in this one, alpha and beta, and in the D'Orazio's work, it's the beta. But each one also has parameters unique to it to characterize the inherent bias. So that's basically how it would work. And the component log likelihoods are generally in their standard forms. So for the presence-only data, that'd be an inhomogeneous Poisson point process model. So okay, let's do that for our lynx data. And what we end up with is with a map that looks like this. And if you compare it to the earlier ones, it sort of looks like an average of these two here, the presence-only data sources. So that's all well and good, but we think that we can do better. So this is where we've extended beyond this to new ground. So there are some common issues that arise in species distribution modeling that aren't really covered in that combined likelihood framework. One is on variable selection. So which of my variables should I include in the model? If I don't know anything about the ecology, I might include uninformative ones. So our proposed solution will be to incorporate a lasso type penalty. There's also the question of diagnostics. I'm putting in these ingredients, these log likelihood formulations, but maybe they're not appropriate for the data that I have. So proposed solution here is to incorporate the likelihood of an area interaction model instead of a Poisson point process model when necessary. So to go into a little bit more detail on those, for variable selection, we can incorporate a lasso type penalty to address potential overfitting. And what in practice we might do is fit a bunch of different models where we increase the steepness of that lasso penalty. When we do so, we end up with what's called a regularization path. So I've graphed 3 of them here, one for each of those individual data sources. And as you go to the right, the lasso penalty increases, and you see that those coefficient estimates are being gradually sucked in towards 0. You can use some criterion like BIC to tell you which model is best. In this case, it's saying for the wild and domestic data, we don't have to shrink at all, choose the smallest penalty. But for the occupancy data set, it's suggesting we should shrink quite a bit. And that makes sense because we had this funky looking map here. All right, so it's saying that that's quite overfitted. So this is something that we can do. Another thing, and perhaps more importantly, is related to model checking. So we're putting in inhomogeneous Poisson point process models for the presence-only data, but that inherently implies that those point locations are independent conditionally in the environment. That may not be the case. There are a bunch of tools that we can use to check whether that's appropriate. This is an example of inhomogeneous K function envelope, which is a simulation envelope, will give you an idea of roughly how much clustering is appropriate for the data that you have. And we see here in both cases, especially for the domestic model, the value of the K function in red is well above the simulation envelope, suggesting there's more clustering than we would expect. That represents a violation of that independence assumption. So that inhomogeneous Poisson point process model likelihood is not appropriate. But thankfully, there's a rich suite of point process models we can use. One of my favorites is an area interaction model because it can accommodate both clustering and point repulsion. The idea is to include an additional covariate essentially called point interactions. And these are essentially going to soak up the spatial signal in your data set. You put a circle of a given radius around all your points, and the point interaction, so for this blue one, it'd be the proportion of that blue circle which overlaps with the other circles. And that way you get the spatial signal picked up. Once we've identified that there is this issue, we might then wonder, well, what might be the cause of that clustering in our data set? It could be maybe that we have a missing environmental covariate that's relevant. Could be species behavior. Maybe the lynx like to hang out. Or it could be an artifact of the observation process. So if I like lynx, and I know someone said I've seen a lynx at location X and Y, I might go near X and Y to look for lynx, right? So one way that we could maybe deduce what the cause might be is to look at that K envelope across our 2 presence-only data sets. When we did that, we saw that the observed value of the K function was comfortably within the range. And that to us suggested that it was the observation process, because we'd expect with the missing environmental covariate or species behavior, the clustering to manifest across the data sources as well. So with this in mind, our proposal is a penalized combined likelihood model. Like the Fithian and D'Orazio models, we fit a combined likelihood expression, which is the sum of the log likelihood components, and we've attached this penalty term P of alpha and beta. So the species data for all D data sources is collected in this list Y here, and each of our data sources determines the form of the source likelihood. So if it's presence only, it could be maybe an inhomogeneous Poisson point process model or presence only. If it's occupancy data, you could have the occupancy likelihood expression. Alpha here collects the bias coefficients unique to each of the data sources, whereas beta collects the environmental coefficients that are informed by all D sources. So all the data is going to inform the environmental signal parameterized by beta, but the unique bias is going to be characterized by the individual alpha. And P, as I mentioned, is a penalty on model complexity. We've looked at both lasso and adaptive lasso there. So applying this to our links data, on the left we have just the standard combined approach. And on the right, we have the approach when we use the area interaction likelihood and the lasso. And we see it's a dramatically different picture. We see a lot more areas of excitement, if you will, for where the links might be. So we've ended up with quite a different map. But that might raise the question, is it a better map, right? So to test this, we set up some simulations. And to do so, we just defined a large species pattern from a Poisson intensity surface based on 4 covariates. We then subsampled 2 different biased presence-only patterns of different sizes and with different degrees of clustering. We also generated a site history to use as an occupancy model. So we sort of mimicked the design of our real data set. And then we fit models using the meaningful covariates, the biased covariates, and 4 dummy covariates, which were uninformative. And we alternated the form of the penalty and the presence-only likelihood component. And the results here, so on capturing the true intensity, this is integrated mean square error. So lower is better here. The blue represent the Poisson likelihoods, the orange, the area interaction likelihoods, and the lighter colors mean more penalization. We see if there's no presence-only clustering, if we wrongly include an area interaction term, we're not actually penalized at all for that, which is interesting. But if there is clustering, you see this benefit of having the area interaction component. Inclusion of the lasso penalty is more beneficial when you've got smaller data sets, which is not surprising to us. So it seems like our approach does better than the standard combination. And the reason for that, it does a better job of estimating the parameters. So these are the true parameter values in green. And what happens is as the sample size increases, the parameter estimates drift away from 0. So that gives a stronger environmental signal than there should be. But by incorporating the area interaction model, when there's clustering, that brings that back in a bit. So that's all I have for you. Just some acknowledgements. This is Olivier and Julie, us doing karaoke in Barcelona. So I've had a lot of fun working with them. Thank you all for your attention, and I'm happy to answer any questions you may have.